Yeah. So, for instance, this degeneracy result, when the form is non-degenerate and you have V and V prime two vectors such that its inner product with every vector is same, then V and V prime are same. Okay. So in particular, for instance, we used it to say that if V comma W is 0 for all W in V, then V must be 0. Yeah, you can apply it to the case where V prime is 0, for instance. Yeah. So the proof is pretty straightforward. So let's see. So 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 you consider so proof is we know that V comma W is same as V prime comma W for all W in V. Then this implies that if you uh, uh, take the difference and use the fact that it is additive in both coordinates, so you are using additive in the first coordinate, then this is 0 for all W in V. So this implies now in particular it tells you that V minus V prime comma V minus V prime is also 0. Yeah, so because it's true for all W in particular, which implies V minus V prime is 0, because you are oh, sorry. So I started using the fact that it's positive. Non-degenerate means that if this happens for all W in W, then V minus. So from here itself, you can conclude that V minus V prime. Positive definite means that inner product with itself is positive, but this non-degenerate just means that in this case, this is 0. Yeah. If inner product of something with every vector is 0, then that vector must be 0. Yeah. So that implies V equals V prime. Right. So this is not at all difficult. And similarly, there is this projection formula statement I haven't written completely. So let this be a symmetric form on real vector space V or a Hermitian form uh, on a complex vector space V. So as I said, these two, we proved some results for symmetric and some for Hermitian. And I said same result holds for, those results hold in both situations. Yeah. So in Artin, he's doing it simultaneously for both, because the same idea, same proof works. Yeah, whether you are thinking of it as a symmetric form on a symmetric bilinear form on a real vector space or a Hermitian form on a complex vector space, so the same thing works. Yeah. So let W be a subspace of V on which the form is non-degenerate. So once the form is non-degenerate, you can find an orthonormal basis. So let W1 to WK be an orthonormal basis of or in fact, maybe I'll write a more general formula. So let's say it's just an orthogonal basis. You can choose an orthonormal basis, but let's say orthogonal basis of W. Then since it's a non-degenerate form on W, then you can find an orthonormal basis. But let's just say, sorry, if it is a positive definite, then you can find orthonormal basis. As in general, you only get an orthogonal basis. So the self-inner product may be 1 or -1 if it's if it's not a positive. Yeah. Then then there is a projection formula. Yeah. So then um, then the projection, then if okay, so maybe I should write it this way. Let P from V to W be the projection of V onto W via. So remember, we proved this, that if this happens, V is a subspace on which this inner product is non-degenerate via the isomorphism. So we proved that V is isomorphic. V is equal to, actually not isomorphic, but internal direct sum. Yeah, V is internal direct sum of W and W per. Yeah, so once you write it down, you know what this projection is. So P is basically, you have a map from V to, so V is equal to W. So you just look at the map from W plus W per, you'll have a projection onto W. Yeah. So W and then the inclusion of W. So this is the projection onto W. Let's call it PW, and then the inclusion of W in B. So this composition is what P is. Yeah. So P is the composition of these two. But what I mean, there is a formula for it. You can compute it. So P is, first you apply PW and then IW. Yeah. So then PV, this is so for V in V, the formula is that you look at the inner product of V with WI and divide by the inner product of WI with itself and multiply by WI. Yeah, so the scalar, you sum this over I equals 1 to K. The K vectors. Yeah. So then PV is this for all V in V. Okay. So PV has to be an element of W. So I'm giving you a formula for what PV is. Is the statement clear? P a map from V to V or V to W? P is a map from V to V. It's a projection operator. Yeah. So it's a map from V to V whose image is W and the kernel is W per. Okay. So P is the projection operator. Maybe I can write operator. Yeah. So you remember we were doing this projection. So projection operators are endomorphisms of V such that the square is itself. Yeah. P square is P. Then you say it's a projection operator. And then it's determined by what its kernel is, essentially. Yeah. Projection operators. So here, since we know that V is W plus W per, so in fact, you can take any complementary dimensional subspace of any complementary subspace of W, and that will lead to a projection operator. But if you have a Hermitian form or a symmetric bilinear form, which is non-degenerate on W, then there is a natural complementary subspace, which is W per. Yeah, and this projection is with respect to that subspace, and then the formula is this. So Let's see if I can move this below. Yeah. Okay, so now, so let's see a proof. So this also we sort of saw the idea behind it, but the statement maybe not. So the idea, so what you do is you want to show that PV is, uh, so of course a PV is this. So of course, um, um, what you have to do, so any vector in V given in V, you can write it as some element in W and some in W perp, yeah? So uniquely, then V equals, um, let's say PV, the projection onto V plus um, V minus PV, where this is in W perp and this is in W. Yeah. So whenever you have this direct sum, since V is W direct sum W perp. Yeah. So you can uniquely write it like this. So all I have to show is that this sum satisfies this property. Yeah. So this formula, of course, is in W. So to check that V minus PV is in W, so all I have to do is check that V minus PV is in W per. Yeah. So, so enough to show. So V minus PV is in W per. I will have to show that is orthogonal to, so W part was the space which is orthogonal to every vector in W, but that is equivalent to saying that it's orthogonal to the basis. Yeah, once it is orthogonal to the basis vector, then it has to be orthogonal to every element in W. So let's just check that. So the inner product of V minus PV with so extra comma V minus PV comma WI. Let's compute this. Yeah. So this is same as, so you just apply this formula. So or let's write it as PV minus V. Is okay. It doesn't matter. Yeah. So by um, so I'll use in the second variable, then it's easier. Yeah, then I don't have to conjugate. So Wi comma V minus PV. So meaning I have to allow it to be Hermitian. So in second variable it's linear, yeah. So I don't have to do any conjugation. So let's just compute this. So this is inner product with Wi, and these coefficients come out. So I'll just write it in one step. So I equals 1 to k v comma, okay, let's call it wj, because we are trying to so we are trying to compute this for every j between 1 and k. Yeah? So v comma wi over wi comma wi. This is the coefficient of wi, and then we are taking oh, it's v minus pv. So there will be a negative sign. 1 minus v minus pv. So sorry, so maybe I have to do it with v and pv. Yeah, so let's just so it is wj comma v minus summation wj comma pv. So that I can write it this way: v minus v comma wi over wi comma wi I equals 1 to k, and then the inner product is with wj comma wk, wj comma wi. Is this okay, the formula? Yeah. So wj comma v minus pv is just wj comma v minus wj comma pv, and wj comma pv I've just expanded. Use the formula for this thing. Yeah. So we are trying to yeah. So maybe yeah, it looks enough to show that yeah. So this looks like a cyclic argument. So so what I meant was less. So PV has a definition, yeah. So I just want to say that PV is equal to this. So maybe let's write it differently. Yeah. So let's call this right hand side as something. Otherwise, it looks like a. Um, uh, so um, yeah. Sorry. Maybe. So let's. Um, um, let we um, v bar be the right hand side of this formula. Yeah. So summation I equals 1 to k v wi over wi comma wi for all v. Sorry, this is not needed. Yeah. So let v bar be this. Then um, what we know is that v bar is in w. So so if we show uh, v minus v bar is in p is in v minus v bar is in w perp, then PV is V bar. Yeah. So that is the definition of PV. PV is that element of W such that V minus PV is in W bar. Yeah. So what we have to do is that we'll have to show V minus V bar is in W per. Yeah, because it's by definition it is in W. Yeah. So enough to show V minus V bar is in W per, and now it doesn't look very cyclic. Yeah. So V bar, and of course V minus V bar, Wj comma V minus V bar is Wj comma V minus. So I've just written down the formula for V bar on the right hand side. Yeah. Now it is. Is it okay? Yeah. And this of course is so remember it's an orthogonal basis. So wj comma wi survives only when j equals I. Yeah. So this sum is basically wj comma v minus v comma um, I see. There is a order missing, yeah. But it is symmetric and the other one is Hermitian. So this should be okay. Um, but okay, let's just write it down first. Yeah, so this is Wj. So the only term which will survive is when I equals j. Yeah, so let's just write this Wj over. So this two will cancel out and you'll get just this. Yeah. So, so for symmetric form, this is zero, but for Hermitian, this is not zero. So what? Say that again. Hermitian form it would be not zero. Yeah, yeah. For Hermitian, this is not zero. So maybe I have the formula wrong. So probably it's Wi comma v. Yeah. So the conjugate will come up if I write it this way. So it's probably yeah. So let's just change the order. Wi comma v. So for symmetric it doesn't matter, but for Hermitian it does matter how you write the. So yeah. Why is it blue suddenly? And so it should be Wi comma v. Yeah, and then you get that this is, then this is okay. Yeah. And, yeah, it's zero. Okay, so this is zero, hence uh, v minus v bar, and this is true for all j. Yeah, so for all j between 1 and k. So this tells you that v minus v bar is in W per, hence PV equals v bar. Okay. So this completes this projection formula. So this is also useful in, so this is like a Gram-Smith orthogonalization process. Yeah. So if you are given any basis, then this is the method you use to orthogonalize to get an orthogonal basis. Yeah. You start, so if you are given any basis on a Hermitian space or a Euclidean space, so space with a non-degenerate bilinear form or then what or sorry, positive definite bilinear form or a positive definite Hermitian form, then you start with one any basis vector and you scale it by its length to um, get it to a unit vector, and then the next vector you sort of find you make it orthogonal in the sense that you remove the inner product from it and so on. So there is something called Gram-Smith orthogonalization. So maybe that I'll put it as a homework, how you can use this formula to convert any basis to an orthogonal basis in a reasonable way. And then, so maybe I mentioned it, the spectral theorem for normal varieties also give you spectral theorem for unitary, um, unitary, maybe I can. So I can move this, yeah. Okay. So part okay. And it looks like it's solved. Yeah. So if a unitary matrix, as we know, is already normal, so you can apply it to any unitary matrix, and that tells you that that you can diagonalize it by a unitary matrix. So this corollary is so uh, A follows from um, a unitary matrix from the fact that A is unitary, then A is normal, and that spectral theorem is true for normal matrices. Yeah. So you can find a unitary matrix such that P star AP is diagonal. And then remember unitary matrices. So the property of unitary matrices is that A star is identity. Yeah. So A star is identity. A unitary. So of course, unitary matrices form a subgroup of GLN, which is called the unitary group. So what it says is that so A implies that every conjugacy class A implies B. Yeah, so this is clear. So every conjugacy class will have so if you start with any unitary matrix, you can find another unitary matrix P such that P star AP is diagonal, uh, and P star is same as P inverse. Yeah. So if you conjugate, that means every conjugacy class. So the conjugacy class of A contains a diagonal matrix. So that tells you that every conjugacy class in the unitary group contains a diagonal matrix. Yeah, is that okay? So there is nothing deep in this result. It's just some observation. Yeah. Okay. So somehow. Is that fine? Yeah. Yeah. Okay. I'll have to close this. It's acting up. So try to restart this thing. OneNote. Yeah, I haven't shared yet. Okay, so these were some easy observations and some missing things from last time. So now we will get to some applications of um, um, spectral theorem. Yeah. So you can see the screen, I hope, yeah? Yeah. So let T be a normal operator. So I'll begin with some terminology, yeah? So let T be a normal operator on a Hermitian space V. The spectrum S of T. So spectrum is a subset of real or complex, so maybe complex number. So spectrum is some subset of complex numbers. So spectrum of this operator, normal operator, is the set of eigenvalues of T. Yeah. So S is lambda 1 to lambda k. So when you do functional analysis, then your operator will be on a bigger space, some Hilbert space or some Banach space and stuff. Then the spectrum may not be finite set; it may be bigger. Yeah, but I'm just telling you so that when you do functional analysis, you can connect with that idea. Okay, then. Yeah, so you can write W. So of course, V you can write it as dx. So we know that if T is a normal operator, then it is generated by it contains an orthonormal basis consisting of eigen vectors of T. Yeah. So you can write V as dx sum of Wi's, where Wi is the lambda I eigenspace. Yeah. So if you take, so Wi will be lambda I eigenspace, and in fact, you can choose an orthonormal basis of Wi as well. Yeah, with respect to this pair. And so let Pi be the projection operators like we did earlier. Then I is P1 plus P. So then so okay, so maybe okay, so this requires a little bit of justification. And T is, so I didn't write, okay, so I should have given a proof, maybe, even though it's a short proof. And then maybe I'll define non-decade, so maybe I can use this space to do a proof. Okay. So let's see if I can. That's not good. Okay. So I'll first show this statement. So it's definition and then followed by something. So so it follows basically from the fact that we have a basis consisting of eigenvectors of T. So let me move this below a little. Little more. Yeah. And then we'll prove the theorem. Okay. So yeah, so let's so maybe this is some observation. So this is where the definition of spectrum ends, and this is the observation. So let use this, and so proof. So of course, PIs are projection onto WI. So you can so I guess if V is in V, then since there exists, so you can write V as W1 to, I don't know how many eigenvalues, lambda k. So k eigenvalue, I equals 1 to k. Yeah. So W1 to Wk, where W1, Wi belongs to capital Wi. Yeah. And since T is normal, since T is normal, the inner product between Wi and Wj is going to be 0. Yeah. So, so if you have two different, if you have eigenvectors with two different eigenvalues for a normal operator, then this is 0. So this is a homework problem. So basically, um, I mean, you can find an orthonormal basis consisting of eigenvectors of this. So, so now if the idea is if something is in W1 and something is in W2, then they better be orthogonal. Yeah, there can't be any relation between them. But anyway, this follows from some a homework problem which says that for a normal operator, if you to take two eigenvectors with different eigenvalues, then their inner product must be 0. Okay, so they are indeed orthogonal. And so, what is PV? Sorry, what is PI? So now note that PIW is just W. Yeah, PIWI is just WI, and PIWJ is